Okay, example 11. A cylindrical soft drink can is to be constructed so it will have a volume of 21 cubic inches. Notice that this is maybe not noticed by you guys as much as it is by me, but fixed volume is important. So anytime you're trying to do any kind of optimization, which is what this is, and we're going to do optimization in calculus using calculus, we're doing optimization here using algebra and our calculators, but anytime you're optimizing something, they're going to hold something constant. They're going to say this has to be what is. So it has to have that volume. We have to fit enough drink in it, basically. But we can have the can constructed in any way, shape, or form as long as that volume is happening. And they have a basic idea of how to make this can. They want a cylindrical soft drink can, so we're assuming just a regular can. We're going to pretend it's just a normal cylinder. It's not going to have any kind of indentations on it or anything like that. All right. What they want to do is they want to write the total surface area of the can as a function of r, where r is the radius of the can in inches. Okay. So let's start off with this. If I've got just some generic drink can that's in a cylindrical shape like so, okay, and the base has a radius of r, which is what they told me, and the height is some unknown height, which is a different value than r, maybe, I don't know. There's no way to determine that it is the same, so I'm going to assume it's different, so I have to use a different letter to represent it. I want to draw my drink can with it drawn like that, with any dimension that's allowed to change as a variable. So I'm allowed to have any radius, I'm allowed to have any height, so both of those dimensions are allowed to change, so both of those dimensions have to be established as a variable. Then I want to take my fixed information here in order to limit the number of variables in the problem. Right now we have 2. I'm going to use my fixed information to limit myself down to 1, specifically r. Okay, I want h to get out of there. So I have to put h in, there's no way around it, but I can use a fixed information like this in order to get some letter out of this problem. So if I'm dealing with a basic volume of a cylinder, the area of the base is pi r squared, the height is h, right? We're told the volume is supposed to be 21.6 cubic inches. So 21.6 is equal to pi r squared h. Therefore, h is going to be 21.6 over pi r squared. And for the sake of making this problem a little simpler to look at, I'm going to divide 21.6 by pi. I'm going to approximate to 4 decimal places, so 6.8755. Squared. Okay, so 21.6 over pi made this number, and the r squared is still on the bottom. All right, and again, that's a necessary step in this problem. It allows us to, instead of having 2 letters to deal with now, I've only got 1 letter. Instead of h, I'm going to put on this picture 6.8755 over r squared. And again, that's priority 1. Every time you do a problem of this variety, the very first thing you want to do is you want to draw a picture of your item, whatever it is, establish variables to represent the dimensions that are allowed to change. If you're dealing with a box that has 3 dimensions, they usually tell you like the width has to be twice the length or something like that. That allows you to use like x and 2x, 1 letter to represent those. Everything else is usually just 2 dimensions you have to deal with. Anyway, and get that done, and that's the whole reason that volume of 21.6 cubic inches is there. All right, now, at this point, I'm going to shrink this because I don't need it in the way. Just throw that over there. I'll make it red so it stands out. All right, looking at that picture, I'm trying to write the surface area of the can. We know surface area of a cylinder is, the surface area formula is 2b plus pH. So if I go back to this drink can again, the area of the base is b, and this drink can has an area of pi r squared for its base. The perimeter of the base circle, radius of r, is 2 pi r, And the height of the drink can is 6.8755 over r squared. I just noticed something. I just changed my mind about this. Hold on. I'm going to go back to 21.6 over pi r squared. You'll see why in a moment.
Oh, we're going to apply as normal.
Pi's are going to cancel when we multiply, so it's worth doing. So anyway, that's what we have. So if I go back to my surface area formula, B in terms of R, P in terms of R, H in terms of R, everything is in terms of R now. So if I go over and substitute B, P, and H with all these R expressions, I'm going to get surface area A in relationship to R. So, and they're using A for surface area instead of SA, so I'm just going to put A there. So A equals 2B, and B is pi r squared, plus pH, that's 2 pi r times 21.6 over pi r squared. And if I simplify that as much as possible, I get 2 pi r squared. And then this pi cancels that pi. That's a whole number structure. That's the denominator. They're the same thing, so the pi's cancel. And also, this r cancels one of these r's down to an r to the first on the bottom. All right, so we're left with 2 times 21.6 on the top, which is 43.2 over r. So our surface area formula is right there. Now, what we want to do when we're optimizing a drink can, or for that matter, any type of container, is if we have a fixed volume, we want the surface area to be the smallest surface area possible, because surface area represents how much you're going to be using in materials. So if you minimize the surface area, you're minimizing the cost. If, on the other hand, you have a specific surface area you want to use and you want to maximize volume, so you either want to set the surface area at a set thing, you want volume to be the most, all right, or you want the volume to be set and then surface area is the smallest. One or the other. Those are the optimal things for containers. What it asks us for part B, and again that's the end of part A there, there's my surface area formula. Surface area in terms of R. So surface area A equals a bunch of R stuff over here, done. All right. Part B, use a graphing utility to estimate the value of R rounded to the nearest tenth of an inch that produces the minimum surface area. So we want to know what the radius should be. So we go to my calculator here, type in my equation, x's instead of r's, because my calculator doesn't know what r is. 2 pi x squared plus 43.2 divided by x. Notice the divided by x makes it a rational function. We're dealing with a real world example here. The radius represents how big the radius should be. Obviously 0 would be the minimum. Can't have a negative radius. I don't know, I'm looking at a regular drink can, it's not very big, this is in inches, so as far as my window is concerned, I'm going to start at 0, maybe go to 6-inch radius, so I'm thinking of a drink can with a 6-inch radius, like let me drink this, that's probably not right. So obviously the answer should be between 0 and 6 based on my own experience here. As far as the y min and max is concerned, we're talking about surface area here, I don't know, 0 would be the bottom, I would maybe, let's go 20, 30, I don't know, somewhere in there. Let's go 30. Hit graph. As long as you can see the bottom of the graph, you're in good shape. We're looking for a minimum. Did I hit graph?
It only graphs on the other side. Like if you zoom 6, it's all negative.
2x squared, 2 pi x squared plus 43.2 over x.
In parentheses?
Maybe I didn't go high enough. Let's go up to 100. There it is. All right. I didn't go high enough. All right. So, yeah, 30, it was over there, but it's all the way up there. So the bottom of the graph is right there. That's what I'm trying to find. And again, we're trying to find the minimum surface area. The graph, the y coordinate of the graph represents the actual surface area. So we're trying to calculate. So second calc, choose 3 for minimum. And it's left bound, right bound answer. 0, 1, 2, 3, 4, 5, 6. The answer looks to be between 1 and 2 based on my vision. So if I go left bound 1, which is too small, right bound 2, which is too big, and the guess somewhere in between 1.5. We get 1.509231, so 1.5 to the nearest tenth of an inch. So the optimal radius will be 1.5 inches. Just for curiosity's sake, let's see what the optimal height would be, because they might ask for that also. Estimate the value of r to the nearest tenth of an inch that produces the minimum surface area. What would the height be? All right, if I want to know what the height is, 21.6 over pi r squared, using that r that we just found, right? So if I type in my calculator, 21.6 divided by parentheses, was it pi r squared? I think so.
Yeah.
Pi r squared, yep. So pi times 1.5 squared, 3.06 inches would be the optimal, so 3.1 inch would be the optimal height. They didn't ask for that, but they might. So if they do ask for more than one dimension in the final answer, know that you can find the optimal letter that's here, then you have to use whatever type of things you modified over here to allow for that, to find any others.